review of anatomy. It's all pretty straightforward anatomy. Definitely things that we want to be sure that we remember really well would be that cranial nerve, right? Vestibulocochlear, which was what number? I keep doing this to you guys. What is the cranial nerve number? 8. What? 8 or 9? Neither one? Not 8 or 9? Huh? Could be. What was Vegas? Vegas was 10. Okay, we know that. So we're thinking 8, right?
Yeah, 8.
Okay, so 8, I think we agree on 8? Okay, okay, I think we can agree on 8. Okay, good. Woo! Awesome. Huh? Woo! What was 9? Since that was the one that, like, some people were not sure. Oh, yes. Of course. Okay, glossopharyngeal. Good! Good. So let's for sure be sure that that's back in the head. And let's kind of get this out of the way. I know we talk about it in anatomy, but let's just review, because maybe this little bit here is on the border of anatomy and physiology, but this eustachian tube or pharyngotympanic or auditory tube, all those names are the same. Look at this connection, right, between that middle ear, where the bones are, over there, and what would be down here if we were to continue this picture. We've got a connection. The throat, or maybe like official anatomy name, pharynx, right? So we'd have pharynx down here. And we do have this connection, and that connection, when it is open, you see how air, right? Because if this is pharynx, of course, that has a direct connection to the outside, right? So if we've got a direct connection to air out here, right? We could allow air to enter. You see that? And enter all the way into this cavity. But we do have this, right? Tympanic membrane, let's remember that, or eardrum, closing off this connection, right, to the outside through here. So this is closed, right? So we can't really escape out that way, but we could escape out this way, or you could say enter in, right? That would be the same. So yeah, let's talk about that. So what is that thing when, let's say you go up to altitude, right? Especially, kind of quickly, and oh my goodness, and then you feel like your ears are going to pop, right? And then what do you do to make them pop? Yeah, you could like hold your nose and blow. What else could you do?
Move your jaw.
Chew gum. Huh?
Move your jaw.
Move your jaw, right? You could swallow also is another one, which is kind of chewing gum, also like all that saliva and the whatever, and swallow. So, I don't know, what are we doing when we do those things? This is the deal, let me give you a hint. Before you do those things, this tube is actually collapsed so that it's closed. And let's say there was at some point before you started the ascent. Let's say we're on an airplane, right? Let's do the airplane. So you're going to take off. So right before that happens, you were, talking or whatever, right? And so, or swallowing, whatever. And so for a few moments, this opens, right? And then when you're done talking or swallowing, whatever, this will just collapse. And that's normal, right? That's normal. So whatever air had traveled, right, when it was open, there's going to be still some air, of course, in this cavity, because this part, you see how they made it kind of pinkish, right? So this pinkish part is the part that can collapse because it's soft tissue. And this, remember, is bone. Good, carved out of what bone? Anatomy review. Oh, good, temporal bone. All right, so we're going to have some air that, let's say, got trapped, right? You can think of it as getting trapped. So we will talk much, much more about air pressure in the respiratory system, but let's say for now there is a certain pressure in the air around us, right? And we'll save all that for respiratory system. But we'll have a certain air pressure here outside at sea level. And so if some of that air from the outside enters in to here, you see how that pressure would be the same as outside. Like our bodies don't change the pressure, just by entering into a cavity. Good? All right, so we close this down. We've got a pressure here that is equal to the pressure here, air pressure, because we haven't changed anything, right? So it's equal on both sides of this membrane. And then we go up, right, take off, and the pressure outside becomes less, right? Just the air pressure outside, like on the earth, right, becomes less. So now we've got a differential in the pressure. We have our original air pressure, right, and now we have a lower air pressure. So we'll also learn in respiratory system that when you've got a difference in pressure, wherever it's higher, it wants to go to lower. So it'll push. Just like we already know about concentration, right? If you have a higher concentration, it wants to go. Things want to travel to the lower concentration, equal everything out. So same with pressure. Higher is going to want to somehow release itself and equal it out, right? So that's that thing that you're feeling, oh my goodness, when you take off or you go up in an elevator or whatever, right, is this pressure, which really was your original pressure here at sea level, right, compared to now this new pressure outside, which is lower, the air pressure outside, lower, and this air wanting to move to the area of lower pressure, but it can't because you've got this eardrum physically blocking. Good? So the way to release that is to, remember we said that this was collapsed down, which is totally normal, like while you're just like, right, like this. And if you just pop it open, you see how you can, this air now has an escape route, right? And it can exit, and then everything's equalized because you've also allowed, right, all this stuff to kind of just happen, this movement of air. Does that make sense? So, and we just feel that as that pop. Good? So that's all that is. And I think that's it. Let's see. So here's an extreme close-up of an anatomy review, and we're going to add some details to the anatomy so that we can talk about the physiology. The things to focus on for physiology would be this unraveled cochlea. Remember that was more like the snail shell shape, like for real. That's what it's supposed to be. But here in this picture, so that we can more easily see what happens, the artists, right, and the editors have unraveled it. In real life, it's not going to unravel because, of course, it's carved out of that bone, right, that temporal bone, like we just mentioned. But here it's unraveled so that we can see and learn, right? But in real life, keep in mind, it's not going to what are those big blow things like at a party? It's not like that. All right, so I just realized, oh yeah, it's kind of like that, but it's not like that. So just so we could learn, right? So we could see. Okay, so here are the things that are important for anatomy. Let's look at, where's my stick? Oh, brother. Jeez. All right, oh, sorry, I'll find it later. Let's look at cochlear duct. Cochlear duct. So you see this, this slightly darker purple, right, compared to the outer slightly lighter purple. So I put a star next to that because we're going to really focus in on that. And that structure is going to be filled with endolymph. And I think in anatomy, we talked about endolymph and perilymph, right? So let's put that back in our heads right up front. So we've got this endolymph, and here's the thing that we're going to add for physiology because it's going to become important. That's why I have so many stars, right, asterisks up there. The composition of this endolymph, of course, there's going to be a lot of water, just like everything else, a lot of water. But we're going to put stuff in the water so that the overall composition of this endolymph is very close to cytosol. Cytosol of you know, any of our cells or most of our cells. All right, so we'll keep that in mind. And here's a reminder, cytosol, right, once we've established like a resting membrane potential, let's say, right, is going to have high potassium on the inside and low sodium on the inside. Because remember that sodium-potassium ATPase pump, right, what it just did to establish resting membrane potential. We know all that stuff. Good? All right. So let's for sure keep that in our heads. And then let's look out here, right, at sort of the lighter purple area that is continuous, right? If you go out to the tip, remember there's helicotrema, which is the little anatomy thing where we take like a sharp U-turn, right, or a hairpin turn over there. And we've got our two scala, kind of like levels, right, two levels. And in both of the levels, because that's going to be continuous, we've got that perilymph that we mentioned, right, perilymph. So let's look. Composition, of course, a lot of water, but we'll add some stuff to it, and that's going to be the same as CSF, cerebrospinal fluid. Good. In fact, it's continuous, right, with all the areas that contain CSF. All right. I kind of put in some details. I know we have not talked about the composition of blood yet, but you can compare perilymph's composition to the composition of plasma in blood. So we've got a little bit of details in there. Good. So that one maybe we might tuck that in the middle of our heads, right? Because that'll come back to haunt us. This is the one for sure. That's the biggie. All right. So let's see, before we leave this slide, let's look at one more thing. Just this little detail here, right, where that stapes is sort of kind of resting against this little membrane here at that oval window. And when we have a vibration here at the tympanic membrane, the three ossicles will vibrate in turn, and ultimately we'll get that stapes kind of banging or knocking on the oval window. And because this is all fluid in here, we're going to create some fluid waves. So this is how we are going to start the process of transducing sound waves in air, right, because air is on that side of tympanic membrane, into waves in fluid. Good? Waves in fluid. All right. So, let's see. Okay, so this shows us with these dotted lines a little bit of that idea, right? Tympanic membrane moving, bones moving. We kind of tap on the oval window, and now we're going to create waves, right, in this fluid over here. We'll go to the end, we'll make our U-turn, right, and then waves back here. So you see the arrows, right? So we have waves being created this way. Take our U-turn, and then those waves are just going to continue, right? They're just going to continue and come back this way. So far, so good? All right. When we create waves here, right, in these two scala with the perilymph, right? Let's notice how, remember this was cochlear duct, right? Let's also remember this basilar membrane. That's kind of like our membrane that is the enclosure for that cochlear duct, right? So it kind of holds inside of it all that endolymph. So when we have waves in the scala, they're showing you with these dotted lines, you see how this basilar membrane will move, right? All right, so these perilymph waves will create wave-like movements of that basilar membrane. So you see how when we do that, this whole entire cochlear duct, right, is moving. Okay, here we go. Let's see. So now in this picture, they've rewound the cochlea, right? They put it back together and sliced it over here. And now they're taking this rectangle and we're getting the blow-up view of that. And let's orient ourselves. We've got our two scala. See the one on the top, one on the bottom. Remember perilymph, right? And here's the cochlear duct, right? Over there, and that's going to be our basilar membrane. Now here's the extreme close-up of what's inside that cochlear duct. Remember that's endolymph too. All right. So now here's our extreme close-up. So this is technically it's anatomy. I know in my anatomy class we didn't get quite to this level of detail, so we're definitely adding it in right now. So here's our our super close-up anatomy for what is inside, right? Inside that cochlear duct with that basilar membrane, remember, that was going to be caused to move, right? Let's see, what have we got here? The things that I want to particularly draw your attention to would be, you see these cells here and this one there, right? So those are going to be hair cells, hair, not like hair, like this, but they, I don't know who did that. Like, who decided, let's call them hair cells? I don't know, actually, now that I realize it. I don't know. But anyway, that's all right. These are going to be hair cells, and you see how we seem to have perhaps some axons, right, coming from the hair cells. So these are our receptor cells for hearing, these hair cells. Okay, great. And like I said, we've got axons leaving those. Looks like we're going to bundle all the axons and exit, right, and become that cranial nerve, right? I don't remember which one. Okay, just testing. All right, so very good. And let's look at the ends of these hair cells. Looks like we've got tiny little projections, stereocilia. So we recognize the word cilia, right? We remember from anatomy what cilia were, and we've also mentioned, I think it was Thursday, when we were talking about like taste and smell, right? Especially for smell, we had those long cilia, and we said, oh, for smell, yeah, we had cilia, but they were not the kind that push mucus. They were just sort of floating in the mucus to receive those odor molecules dissolved in the mucus. So here we've got a different type of cilia. They still use the word cilia, that's okay. And stereo, that makes sense, like for hearing. Good. All right, stereocilia. Let's look at this setup. If this basilar membrane were to move, right, if you were to do this with the basilar membrane, do you see how, because of this setup, right, we've got these cells sort of holding the hair cells in place, right, at a very specific angle, right? And then we've got these stereocilia. You see how those are also at an angle, right? We've got this angle, and then we've got the stereocilia slightly set at an angle. And then those are kind of embedded in this other membrane, tectorial. Tectorial is our word for roof, right? So we've got a roof membrane, tectorial, and kind of holding the stereocilia at this very specific angle, right? And then we've got our hair cells, and then we're holding those in place. And the basilar membrane is doing that for us. All right, so we've got this setup. If we move the basilar membrane, which we said that's what's going to happen, right? That's what's going to happen. You see how we move this whole thing? Because it's all attached to each other. Like we would physically move these things. All right. Here we go. Now we've got an extreme close-up on, let's say, one hair cell. And this happens to have 3 stereocilia sticking up. All right. And then we see, oh, this is a receptor cell, this hair cell. And here we see there's actually a second neuron in this little sequence. We know that's good, that's fine, right? And this second neuron in the sequence looks like it's going to receive a neurotransmitter, right, from the receptor cell, and then we're going to send the signal, right, down the rest of the nerve. Okay, so let's look at some details. Looks here like, you see how they've done that? Like they've kind of bent, let's say. Right, they moved the cell, which we said we were going to do by moving that basilar membrane. So we're going to move the cell, and it looks like those stereocilia, you see how they're definitely bent this way, right? And before it was kind of like this in the previous picture, so now they're definitely bent this way. So we've moved that cell membrane, right? And maybe we're going to have some ion channels embedded in that cell membrane. So maybe by changing the orientation of the membrane, maybe we'll stretch it, right? Like it sort of changes its orientation and its shape. And if we're going to do that, maybe if we pick the right channels, we could force them open, right? Or closed, which means we should choose mechanically gated ones. We haven't used mechanically gated things yet, I don't think. We've used ligand gated, we've used voltage gated, right? And we have not used our third choice, right, which was mechanically gated. So here's where we're going to use. Here's like our first example of where we're going to use mechanically gated ion channels. So here we'll pick potassium. So we've got mechanically gated potassium ion channels. I probably could continue that line right there. Embedded in the membranes of those stereocilia, so that when the stereocilia are bent because that basilar membrane moves, we can open up the channels. Good? All right, so we open up the channels. Okay, when we open up the channels, the potassium comes in. Great. We can create, what can we create when potassium comes in? Graded potential. Wow, awesome. So we can have graded potentials. These arrows over here are representing those graded potentials traveling the short distance, right? From here to this other side of this hair cell, where we've got, we've seen this choice before, right? Voltage-gated calcium channels. So that's how we build our hair cell, right? Is we pick mechanically gated potassium channels, we put them on the stereocilia, and we pick voltage-gated calcium channels, we put them, kind of at the base of this receptor cell, so that when those graded potentials reach the voltage-gated channels, they respond to the voltage, right, and open up. And we know this, calcium goes in, we trigger vesicles, right, to release neurotransmitter, boom, right? We know all this stuff at the synapse. Okay, so far so good. So far so good. Let's see. Let's look at this drawing where, see how now we've got the stereocilia bending in the other direction? All right, so this is how we're just going to close those mechanically gated potassium channels, just by kind of reversing that direction. Okay, so we close. That means we stop generating graded potentials, right? We stop. We can close calcium channels. We can stop releasing neurotransmitter. Good? I think it's very sensible. All right, so far so good. Let's see what else. We know about glutamate, right? What category of neurotransmitter was glutamate in? Excitatory amino acid. Woo! Super awesome. Let's look at this. We have a couple of other details over here. Our resting membrane potential for these hair cells. See how that's different, right? What was our usual? Remember we said our usual for most neurons was minus 70, right? But I did say, well, we'll see some different things in different locations. So here's a location where, let's for sure remember that differently, right? So here we've got resting membrane potential for hair cells in hearing, right? And let's see, here are a couple of things. If we've got loud sounds, so remember loud sounds were those tall sound waves, right, with the high amplitude. Those will lead to bigger graded potentials here, right? And we know from our general discussion of graded potentials and action potentials that if we have big graded potentials, we'll have bigger sums, right? And we can generate eventually more action potentials right down here when we get to this nerve. So we've got that. And as far as pitch is concerned, right? Because we said frequency of those waves, right? Had to do with pitch. So pitch is going, like the pitch that we perceive is going to depend on, well, first of all, the frequency, right? But on our end of things, it's going to depend on where along that basilar membrane, right? Remember we have the coil that we had temporarily uncoiled, right? So where along that coil different hair cells are located will have different sensitivities to different frequencies or pitches, right? So, and that has to do with how flexible the basilar membrane is. Good? All right, so let's see. I think that is.
So, that's where you have the greater potential arrows going down.
Over here.
Okay, so greater potentials don't use those voltage-gated channels, right?
What do you mean use?
Like they usually use ion channels.
You mean to create a greater potential? Well, so far what we've seen, right, we've seen ligand gated, right, and we've seen we have seen voltage gated, right. But so far for creating graded potentials, we've seen ligand gated, right? Like when we first discussed how do you make a graded potential. So here we're seeing our first example of, if we pick this mechanically gated ion channel, that one can still create a graded potential in this location. So it's now an additional way of creating a graded potential. Okay? In this particular location, for whatever evolutionary reason, right, this is how it has come to be.
So there's no action potential in that area. There's no threshold that happens down the
Right. That's going to happen later. Exactly. Here we're just having a little graded, maybe it's big, right? But we're having our graded potentials here, right? Which will tell calcium channels open, which will tell vesicles release glutamate, right? And then we've got a synapse like normal. Same. Receptors here for glutamate doing their thing, creating graded potentials, and then that's going to travel and be summed, and then we can create our action potentials. Good. All right. That is pretty good. Let's see. Let's see. There it is, right? All right. 8. And traveling, sneaking in there. And then, of course, thalamus, as always, and then primary auditory cortex. All right. So, let's see. This is just FYI. You don't have to memorize this, but this is just a table. I thought it was kind of interesting, so I left it in. Just a table of different examples of types of sounds. Basically decibels measures how loud is the sound. So it's just FYI stuff. Like I said, you don't have to memorize. So we're going to move on to vestibular system, which is intimately tied with the auditory system. And we know vestibulocochlear nerve, cranial nerve number 8, it's in the name, right? Vestibulocochlear. And the axons, right, run together. Good. So let's now review that anatomy for vestibular apparatus. Let's see. So remember, cochlea, that's all hearing stuff. So we're kind of done with that stuff. All right, but you see it's kind of continuous, right? All of this stuff, which is all of our vestibular stuff. So just review that. Anatomy. Let's see. And here we have a nice picture to remind us that those semicircular canals, remember we had 3 semicircular canals on each side. This is a reminder that each canal, right, has an orientation in a specific plane. And we've got our 3 planes. So you see how we've got 3 planes on a cube here? So we would have one semicircular canal, and then at a right angle to that, another semicircular canal, and then at a right angle to those 2, another semicircular canal. So this is our orientation in our heads, right, of those semicircular canals.
On the slide before,
Let's see.
I was having trouble picturing where the organ of the cord teeth is located in there. With the hair cells.
Yeah, no, I totally see what you're saying. So the question was, like, how can we orient, right? How can we orient this entire thing, right, which is organ of Corti, how can we orient this in now this picture that we're looking at a couple of slides later, right? So let's take this item, and we've got our hair cells for hearing as a part, right? Part of this organ of Corti. So this, let's work backwards. So we'll put this in there, and you see, I really just can't stand it. Okay, let me find a stick. Let's see. I gotta get a pointer. That's what I really want. Okay. Bring in the one for my cats. All right. So let's see. So we've got organ of Corti, and that you see is resting on top of. There's basilar membrane, and here's tectorial membrane, and here we've got that entire enclosed cochlear duct, right, with endolymph. And here, so that's kind of I don't know, in the middle, I guess we could say. And then we've got our two scala, kind of sort of on either side. So if we take this and we put this back into here, right, which is our cochlea, see we've got, this is just our little cochlear duct, and you can barely see this little green, and there's a little sort of, I don't know if that's orange or pink or whatever it is. That is our little organ of Corti now, inside there, and our two scala over here. And this is sliced. We see that this is part of that cochlea. So let's make the cochlea. So if we come around, we've got our big loop, and then it's cut off, and then we come around again, and it's cut off, and we come around again, and it's cut off, and then we end there. Good? And so helicotrema, like the U-turn, that hairpin turn, would be like right in here. Good? All right, so that's cochlea, and we can see this. See how this is the basilar membrane? This bit right there. See that? And organ of Corti. See how because the cochlea is like this, we could also say, oh, that whole entire thing inside, right, is also, it's also doing this, right? It's also running the length of this this cochlea when you unwind it. So far, so good.
So
Okay, good.
it's really, so it's really just this part right here, it's not this part.
Right. So let's go to what you were just showing. Okay, so now we take that drawing that we had over here on that previous slide, we're going to put that here, right? It's only this part. So inside this cochlea is that cochlear duct, and inside that cochlear duct, basilar membrane, tectorial membrane, and hair cells. And that's organ of Corti. Good? All right, so that's just in here. So now we shift our focus to what's over here, right? Separate vestibular apparatus, but we're going to see there are a lot of similarities in how they work. All right, so let's see. Aha. So here, just a reminder, right? Organ of Corti is going to be sort of running the length inside this cochlea, running the length of that cochlear duct. All right, and set that aside. And this part over here, vestibular apparatus. Well, we do have a little continuous part here. That's okay, they're separate. All right, so, and here we see the cochlear part of vestibulocochlear nerve, right? That's all coming from all those areas along that basilar membrane, right? They're kind of all bundling together, this cochlear nerve. Separately, we're going to see information coming from the vestibular nerve, and then these two will come together, right? Let's say over here, come together in vestibulocochlear nerve. All right, so, and right, you see this? We were talking about the orientation, right, in 3 planes. So we've got one canal running this way, we've got one canal running this way, we've got another canal running that way. So those are 3 planes for the canal. So you could do like a, right? You could go like this. Is there anything like this? This. Let's see. Let's do this because this stands up. You see this? This, and we'll do one more. Right? You see this? How this is kind of like 3 sides of a box? It's like this. Good? And you just put this, shrink it, and then put it in your head. All right. Very good. So, let's see. That's it. Okay. So, here we've got inside, right? Inside of any one of the semicircular canals, kind of at the base, right? Because the semicircular canals were these sort of loops, right? And at the base of each loop, we have this structure. Oh yes, you can see here, right? This bottom drawing, base of each loop or semicircular canal. So we should remember this from anatomy, but let's look up close and put this up front in our heads. Let's see. Looks like also hair cells, right? So we're going to go with the same name. But remember, we've got hair cells in the auditory system, and then now we've got these separate hair cells, same name, different structure, right, in the vestibular system. Right, so hair cells, and they're like the blue ones, and in between it looks like we've got some columnar cells, right? Remember that, all that epithelium stuff, simple columnar epithelium, that hold them in place. Okay, great. And extending upward from our hair cells, again, same name, stereocilia. Again, these are cilia that are not in charge of pushing mucus, but they're going to help us to open up some ion channels, right? Unfortunately, they stuck with stereo, even though this has nothing to do with hearing, right? This is all vestibular information. So maybe that's a little unfortunate, that stereo, but we have to go with it. I don't know, somebody picked it. So, stereocilia. And we remember this hopefully from anatomy, cupula, which is sort of a gel-like arrangement of gel that hold the stereocilia in place. They're kind of extending straight up from those hair cells when your head is still, right? We're not spinning around or anything. So, okay, you see that? Everybody sees that. Look at what this whole entire semicircular canal, the space in here, is filled with. We recognize endolymph, right? So same story as with hearing. Endolymph. Okay. So, I guess it's here. Here we've got a semicircular canal at rest, so we're not moving in that plane, and now we spin, right? We spin in whatever plane we're looking at, right? For that semicircular canal, remember when I built that little part of the box? So depending on the direction that our head spins, that particular semicircular canal, let's do it, let's see, is going to move. Okay. Cool. Check this out. There's like a collection in this drawer of all these different teas. I had no idea. I'm just discovering this now, but look at this. Seriously, like if you come up here, it smells fantastic. Like, what's going on here? Look at this. This is great. What is going on? Seriously. It's like a major stash here. Unbelievable. All right. Oh man, after all that, look at this. McDonald's. All right. So anyway, that's all right. Here's like, please do not remove. But I'm just showing. I'm not like taking it. I'm just showing you guys like, wow. But anyway, I wanted to use this because this would be cool. You see this? Let's make the things. See that? Right? Semicircular canals. Good. So we have our. All right, stay. Let's see. Good. All right. So if let's say, right? Let's say I put it here in my head, right? Kind of like this, more or less. So if suddenly I decide to spin this way, right? You see how, so which one, the yellow, the green, or the blue, is the canal that's going to be affected? If I hold my head up straight, right, but I spin like this.
Blue.
So who votes for green? Because I heard green. Who votes for green? Okay, so we have some people for green. Who votes for blue? And who votes for yellow? Oh, so we have like, it's kind of equal. Like there were some for each. Let's see. I don't know. Remember that each canal. Oh, did I lose that picture? Each canal is a circle, right? And I don't know. Look at the arrow, right? So let's see. We're gonna rotate. You see? So we've got to rotate this arrow. I don't know, like you see how this is going to rotate, right, this way. Let's say this is a canal that's vertical, right, because it's on this thing. So we're going to rotate that canal this way on this screen. We would have to go, in this direction somehow. If we wanted to rotate this very canal that's printed on this screen, right, that's part of this screen. We would have to, you see how you would have to rotate the screen, right? We would have to take this screen and actually rotate it this way. Make sense? To get this canal to move, right? Actually, they're showing you this out in this direction. You have to rotate this whole screen. Does that make sense? So, let's see. Let's try this one first. Let's see. Let's go like this. So let's pretend that yellow, because this is yellow, right? So let's make this, right? And I'm putting it in this vertical plane. And now I have my other two in these other two planes. So you see how to affect the yellow one, right? To get the yellow one to spin, right? We have to go like, hang on. We have to go like this. Right? You see that? You have to go like this. Make sense? If we go like this, it's actually not going to affect so much the fluid. We want the fluid to flow, you see that? Sort of around the tube, right? To get our maximum effect, right? Our maximum stimulus. Good? So this movement stimulates whatever's in here, the hair cells, right? This movement will give us maximum stimulus. Good? This, not so much. You see that? Not so much. So, all right. Now, if we go back to the original question, which was if this is the orientation, we'll keep yellow here, right? Let's put yellow there. Let yellow be this one.
I thought that the blue was the bottom.
Yeah.
Blue is the
blue
bottom.
is the bottom. Blue is the bottom,
So blue
right?
is the one.
Yellow, we're going to make it this one, right? When I'm going to be facing you guys, and we'll make yellow this, right? And then green, I'm going to say, okay, that's going to be like sagittal. Whoops, sagittal. Good? All right, how's that? Okay, we'll make this coronal, right? And we'll make this transverse. Okay. So, I'm not going to do it, but what would I have to do to get the yellow one to go?
Do a cartwheel.
I'd have to do a cartwheel, right? Which I am extremely bad at gymnastics. Extremely. So I'm so not doing a cartwheel because I'm wearing a skirt. So, so you will not see me do a cartwheel. Bad. Scary. Maybe funny, but it would be more scary than funny. So I'll spare you guys. I won't do a cartwheel. But I would have to do a cartwheel, right? Because it would have to be like a sideways thing. Huh? It would be a side, and my face would have to stay that way. Make sense? And I would go like this, my head, right? You see that? Okay, so now that we know that, if I were to do this spin, right? Blue, right? Does that make sense?
Yeah.
Ah, okay. Good. Super good. All right. Let's see. Very good. So, I'll fix this later. Okay, so we get that. You see how, before we leave this slide, you see how if you get a semicircular canal to turn, right? We have this sort of physical movement, but we do have endolymph on the inside. You know how when you have a bottle of water or a glass of water and you spin it and the water inside starts spinning? You know how the water inside that's spinning, it's like behind what you're doing to the glass? It's kind of like that, right? So this endolymph on the inside will start to spin, but it a little bit lags behind. Good, but you can see it will spin, right? And you see how that cupula bends, right? Because the fluid is moving, spinning over it. Huh?
Yellow was doing a cartwheel.
Yellow is doing a cartwheel.
Blue was going
Blue is this way.
and then the green is going to
Okay, let's do
somersault.
Somersault, right?
Yeah.
Let's set that up again. All right, one more time. Right? So the green, if I'm in the sagittal plane, what do I have to do? Somersault, right? I have to do that. But all the way around, so not doing. That would be even scarier than the cartwheel. That's like the worst. Huh?
They're scary.
Oh yeah.
Somersault.
Yeah. Like can't do. So, but anyway, we know, right? Somersault. Okay, good. Good. Let's see. Somersault. All right. Oops. So here's our close-up of these hair cells with their stereocilia sticking out. Turns out the mechanism is the same, right, as with hearing. We're going to bend the stereocilia because we're moving that endolymph, right? It's just the reason we're moving the endolymph is because we're spinning one of the canals, right? All right, so look at that, and it's going to be the same thing. I think they don't show you the details, but it'll be the same thing with mechanically gated potassium channels, graded potentials, voltage gated calcium channels, release, synapse, the rest. Good? More graded potentials and then action potentials. So what they're showing us here are those resultant action potentials, right? Once we get to here, right? The nerve after. We'll have our action potentials. So at rest, turns out in the vestibular system, because the vestibular system, we kind of always need to know, even if we're not doing the somersault, right? We kind of always need to have some level of feedback about, like, where is my head in space, right? As far as spinning, especially spinning is concerned. That would be good to know, right? So we will always have a little bit of glutamate being released kind of as a baseline. Right, so we'll always have a few action potentials just sort of being generated by nature of being like here, right? And kind of awake and aware and holding our head up straight. Just regular. All right, and then let's say we've got a major, so there's the cartwheel, right? Whatever. And boom, 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 boom. A lot of stimulation there. And then when that motion stops, right? Cartwheel is done. I survived, right? Survived the cartwheel. You see how, and we know this from that glass of water idea, right? When you stop spinning the glass of water, the water continues to spin, but then eventually it will sort of slow down, and then stop, and then reverse, right? So this is what we're seeing here when eventually it slows down, stops, and reverses. And then we get everything happening in reverse. Close the potassium ion channels, close the calcium ion channels, stop sending stuff through that synapse, and now we have very few action potentials going through to tell us that whole bit with the cartwheel stop, we're done with the cartwheel. I probably felt that. Good? All right, so wait, I could have sworn someone had a question.
No.
Oh, okay. spinning, and we saw 3 different planes for spinning. Here, we're going to take a look at just moving the head from one position to another position, but not spinning, right? So let's say you are asleep, and then you wake up, and then you sit up. You see how that's acceleration of the head. And first you were here, and then you come up to here, right? So that's acceleration of the head. Or it could be like going from here, and then I move through space. That's still acceleration of the head, right? Because the head moved from like one place to another place. So for here, let's see. Wait, let me just show you the picture. We'll go back to this. We're going to use. You see these patches here? Good. So going back to that anatomy, right in here. Good. All right. Let's see. All right. And let's remember structure. I know we talked about this in anatomy, but let's remember the structure. Again, hair cells, right? We're going to have, they don't even label it, but stereocilia sticking up. And here we've got otoliths sitting on top of some gel, right? Up here. And so this guy they're showing us, he's standing up straight, and he's going to bend forward. When he bends forward, you see how the gel sitting on top of those hair cells, it kind of, right, it just sort of blobs forward. And those otoliths, the little rock things that sit on top of the gel, they keep the gel on so that the whole gel doesn't just like flop off. Like if you had a plate of Jell-O, right? If you tilt it forward, it'll start to like, ugh. But if you didn't have anything on top of it, like holding it in place, it would totally like on the ground. So we're gonna have otoliths to hold it up.
So they're on top of the gel.
Right, on top of
They're
the gel.
not on top of the hair cells.
Right. Otoliths are right on top of that gel to keep it on the hair cells. Keep the gel on the hair cells. All right, but anyway, he bends forward. It looks like he's tying a shoe. And you see everything start to move. And because we've got those stereocilia sort of embedded, right, in the gel, and you see how they bend, same mechanism that we've been talking about. Good mechanically gated potassium channels. All right. Let's see. So, I think that's the last one. Let's see. Looks like, let's go to the bottom first and then we'll go back. As always, thalamus, vestibular cortex, primary. We will see in the muscle control section, we will add information to this information from the vestibular system. We will add information coming directly from the joints, right, and the muscle tendons, and we'll kind of combine all of this information. So stuff coming from the head and stuff coming from joints and muscle tendons. We can put it all together in cortex, various cortices, and then figure out, okay, where is everything in space? Good? All right, so up here, I think if I remember right, in the lab manual, I'm pretty sure they mentioned nystagmus at some point.
Yeah, I didn't know what that was.
Yeah, okay, so I'm pretty sure they mentioned nystagmus, but here we've got a definition of what is nystagmus. So what it is, if you were examining someone and you were to see this happen, this would be nystagmus. Is when the eyeballs, you're let's say examining the eyes, and they'll move like side to side, right, like this, and that's an involuntary movement. So the person probably doesn't even realize. I mean, they might be dizzy or something like that, but it's not like they're doing that on purpose, right? Like, you know how you could, right? You could look like side to side, side to side. It's not that. It's a much finer movement, and it's very quick. Good? And the person can't control that. All right, so that would be our definition of nystagmus. So here we can tie that into this vestibular system. Well, first of all, before we talk about the vestibular aspect of it, We know that to create movement of the eyeball, especially a side-to-side movement, we would need muscles, right? Right? And we talked about those a little bit. We looked at them a little bit last week, right? Extraocular eye muscles. And specifically, we would be using medial and lateral, right? Rectus muscles kind of alternating. Good? Okay, so we know that much. And cranial nerve number what is going to work on those, or nerves? Numbers. Three, which is, what's the name? Oculomotor. The other cranial nerve is named for the action. So think about the actions of the movement of the eyeball. What would be, like if you do my right eye, right? Now I'm going straight ahead. This is midline. If I take my right eye and I look to that side, am I adducting or abducting this eyeball?
Abductor.
Huh? Ab. And isn't there a nerve like
Abductor.
abducens, right? Oh yeah. Alright, it's abducens, right? Cranial nerve number? Trigeminal is 5, right? Because remember, like, even though it was trigeminal, it was like number 5, 3 branches. Oh, 6. I think 6. Not 4. What was 4? That was anatomy. So this is why, A and P is better. If you ask me. But anyway, 4. What was 4? It's also for one of those muscles. Huh? Not trigeminal. Trigeminal's 5. 4, 4, 4. It was for one of those extraocular muscles. It was trochlear, right? It was held in place by that little, right? That little ligament there, right? All right, that's right. That's trochlear. All right. Okay, good. It's a good review. Always good to review. So let's see. Nystagmus. Okay. So on that side of things, right? The muscle, skeletal muscle side of things. Okay, great. So we got that straightened out. What has to happen over there? But like something is going to trigger those nerves to tell those muscles, like, do that, right? That seems weird. So turns out we end up with vestibular input, especially in this direction, right? This whole thing, especially in that direction. For some reason, we just have firing, right? In this semicircular canal, that was our blue one, right? Our blue semicircular canal, firing, and telling those nerves to tell those muscles, go, right? Let's look at one example, right? What can happen? There's alcohol in there. Well, you know about alcohol, right? We know some stuff. Well, alcohol is going to be kind of a common theme. We get to like liver and stuff like that. We'll talk some more about alcohol. But here, nervous system, easy, right, to cross that blood-brain barrier, easy to get into brain, right, and into CSF. If we can get into CSF, we can get into endolymph, right? Because we said that was continuous, right? All right, so if we can do that, like we can diffuse into all of that, we can change composition. It's a chemical, right? Alcohol is a chemical. So we can change that and create the sensations without actually spinning. Do you see it? Unfair. Unfair. So we get firing of those neurons. Oops, we didn't do spinning, right? We just did, look at that. And, so this is why, right? A little too much? sensations. Oops. And then don't drive, but if the police pull you over, right, they're going to look in your eyes. It's not only the ooh, right, but they'll look in your eyes, and if they see, and then the test. All right. So anyway, that's good. Let's see. Good. So that finishes off. Sensory. Woo! Duh. Let's see. How do we got time? Let's do this. Let's do this. Oh, let's give it have a choice. You can either take your break now. I know it's a little bit early for the break. We can either take a break now and do the hearing part with the tuning forks of our lab. You want to do it that way? Why don't we do break? Because then I'll pull out all the stuff. We'll do 10-minute break, and then we come back. We'll do the hearing part of the lab, and then we'll do muscle stuff. Good? Because the hearing part, that's going to be really quick. That's super quick lab. Good? So let's do that. So 9:10, we'll come back, and I'll have stuff set out. So when you come back,